Well, hello Internet, and welcome to part 2 of my assembly language video tutorial. In this part of the tutorial, we're going to cover logical operators, looping, barrel shifting, memory storage, and debugging. And unlike the first part of the tutorial, this time we're going to pretty much only be writing a lot of code. However, if you didn't watch part 1, you should definitely watch it, and I provide a link here in the video as well as in the description. Also in the description, you're going to find a link to a transcript as well as all of the code. So the best way to learn this stuff is to go and get this transcript. It's free, of course, and there's a link in the description. And then you can use this as a cheat sheet to go through and also to take notes on so you can better remember all of the stuffs here, and as well write down any questions you have and leave them in the comments below. So I have a lot to do, so let's get into it. Okay, so here we are in our Raspberry Pi once again, and we're going to be using the same exact file, assembly.tut.s, and here we are inside of Vim. As this tutorial continues, I'm going to show you little neat tricks you can use to do things with Vim, and one of them is if you wanted to delete everything that you have inside here, just hit escape and then colon, and then you're going to hit $D and hit enter. And there you can see everything is gone. And I'm going to undo that by hitting U, and everything's back again. So let's go through here and let's start writing a little bit of code. What I'm going to do here now is talk about logical operators. So we're going to actually be writing some real code here that's going to be more useful, and it's going to start to look more like regular programs. Now, a logical operator is going to follow a format in which you're going to have some type of instruction. And then after that, you're going to have your destination where the result is going to go to, and you're going to have a comma, and then you're going to have an operand inside of here, and then you're going to have a comma, and then you're going to have another operand. So let's go through and do a couple examples, and all of this will make a lot of sense. So down here inside of start, I'm going to escape out of this, and I'm going to hit capital letter V, and then I'm going to select those lines by pressing down on the arrow keys, and then I'm going to delete them because I'm going to do some new stuff. Now I'm in insert mode again, and the first thing I'm going to do is move into register 1 the value of 5, and I'm going to put a comment inside of this, and this is going to represent this binary number, and you need to see that so that you'll understand what's going on here with this conditional operator. We're first going to cover and just is going to only give you a result of 1 if both of the values are equal to 1. So, and in register 2, I'm going to go and give this a value of 9, which is going to be equivalent to 1001, or whatever you see right there. And now we'll use and. So we're going to go and R0, this is going to be our destination. R1 is going to be an operand. R2 is going to be another operand. Let's get rid of this stuff. Escape, capital V and D, and that's all gone. And then we'll hit escape, colon, WQ. Now we'll go make, and you can see this has been assembled. And then we can echo out onto the screen the value of 1. Now, why did we get the result that we got right there? Let's jump in here and look. You can see right here we have 1 and 1. That's going to give us a value of 1. You can see 0 and 0 is going to give us a 0. 1 and 0 is going to give us a 0. And 0 and 1 are going to give us a 0. And that's the reason why whenever we use the conditional operator and, we get a value of 1. So now let's come in here, and we're not going to change that much. We'll just come in and change. Instead of using and, this time we're going to use or, which is another conditional operator, and it's ORR. And as I'm sure you're probably aware, 1 and 1 is going to give us a value of 1, 0, and 0 is going to give us a value of 0. This is going to give us 1, and this is going to give us 1. And you're going to see that that's going to work out to 13. So let's escape out of that, make again, and there you can see the value of 13 comes back once again. And that's how the OR conditional operator works. Now we'll use the exclusive OR operator. Again, just come in here, insert, get rid of that. That's an exclusive OR. Nothing else is going to change. Basically here, we're going to get a value of 0 here, and we're going to get a value of 0 here, and here we're going to get a value of 1 and 1. And of course, that's going to equal out to the value of 12. So if it's 1, 1, 0, 0, that comes out to 1, 2. Neither of those is going to work for us. Then we got 4 and 8. Whenever you add 4 and 8 together, you get a value of 12. Do another make and echo, and you can see 12 shows up. We can clear our scroll back by typing in clear, and there we are. And now I'm going to give you a real-world example. I'm going to use what is called the bit clear conditional operator, or BIC. So let's jump over inside of Vim once again, open that up, and we'll do a quick example, and then we'll do a much more elaborate example just to make this a little bit more interesting. So BIC stands for bit clear. And basically it's going to return a 0 except when the top bit is a 1 and the bottom bit is equal to 0. And like I said, I'll show you an example here where that actually is useful. So it's going to return 0 except when the top bit is 1. So here we got 1 right there. And the bottom bit is 0. So this will end up being a 0, this will end up being a 1, this will be a 0, and this will be a 0. And if we think about what that works out to be, that's 1, 2, and 4. And this is going to give us a value of 4 whenever we go and execute this. And let's execute it, and you can see indeed that it came back that way. So now let's jump into Vim again, and let's write a more elaborate program. Basically what we want to do here is we want to receive a lowercase value and convert it into uppercase. So let's come in, and let's delete a whole bunch of different things. First thing I want to do is to be able to read information from our keyboard, so we're going to be doing a lot of reviewing here. And to do so, we have to set our system call to read from the keyboard, and we set R7 to 3. Now let's come in here and write some stuff. System call keyboard, and then we'll go down and set the register 0 to 0, and this is saying input stream is our keyboard. In register 2, we're going to set that to a value of 1, and we're going to say that we want to read 1 character. After you do this enough, it'll just stick to your head. Then we want to read in our address for our character where we're going to be storing this information, so LDR, and I'll store that in R1 because that's not being used, and we're going to get something called character, and then we will close this off by going SWI and 0. I'll bounce down inside of here, and in our data section we're going to define character and a colon, and we're going to say this is going to be an ASCII, and we're just going to give it just nothing between these two quotes. Bounce back up inside of here, do a little bit more stuff, find another label. This is going to be called uppercase. We're going to get the address for our character, and then we're going to load our character into the 0 register. Of course, we're going to put brackets around this. And then basically what we want to do here is we want to 0 out our 6th bit, and I'll explain exactly why that is. So if we have, let's put a comment inside of here. So if we have a lowercase a, that is going to have a value of 0, 1, 1, 0, 0, 0, 1, like that. On the other hand, if we have an uppercase value for a, that is going to have a value of 0, 1, 0, 0, and 0, 0, 0, 1. So now if we look at this very closely, you can see right here the only difference between a lowercase a and an uppercase a is this bit right here. So if we want to take in a lowercase value and convert it into an uppercase value, all we need to do is get rid of that guy right there. And so to do so, we want to use the bit clear with a value of 32. So all we got to do is go 0, 0, 1, 0, and then 0, 0, 0, 0. So it's going to keep all of our 1s inside of here. It's going to let those all be set, and any bits that we want to get rid of, it's going to get rid of. And you can see there we're only going to get rid of one of them. And to do that operation, it's actually quite easy. All we got to do is go BIC, and we're going to go R0, R0, and the number 32. Why 32? 1, 2, 4, 8, 16, 32. That's the one we're getting rid of. Okay? And then after we do that, we can come in here and store the character with the address stored in R1 inside of R0. So we'll go string and R0, and we're going to put the value of R0 in the address for R1. Okay, so that's all well enough. Let's come in here now and let's output information to our screen. We'll use write once again, and we just have to set our registers properly so that we will be able to come out here and output information to the screen. So we're going to have to make our system call once again, store the value of 4, and this is just system call output to screen, set our 0 register equal to 1, and here define our output as our monitor. Once again, we'll set register 2 to the value of 1, and this is defining the number of characters. Since all we're doing is converting from lowercase into uppercase, that's just going to be 1 character. And then we define the value that we want to print out, which is going to be character. And then we can close that off. And then we can come out of here, and you can see there's end. We set R7 just like we always do. We close that off. Of course, we have our information that's going to be stored inside a character, and that's all we need to do. So we're going to escape. Here, we're not going to be using echo. We're just going to be using assembly tut because it's expecting input from us. hit enter, and let's just do any character. There's D, hit enter, and you can see the capital D comes back. Come back, run it again, you do K, and you can see the uppercase K comes back. And there's more of a real-world example of how we can use conditional operators, and of course, as the tutorial continues, we're going to find even more ways we can use them. Now I'm going to show you another one, and this is called test bits, and what this is going to do is perform an AND on bits, and then update our 0 flag, which we talked about previously. Once again, the CPSR is going to store our 0 flag inside of here, so we're just going to be able to come in there and test for a whole bunch of different things. And as the tutorial continues, we're going to be using these registers a lot more. Let's come in and let's open up Vim again, and I'll show you an example of exactly how that's going to work for us. Let's just go in here and copy out of this and hit $sign and D to clear everything out, and let's just start fresh. So global start, and then define start, throw some information in register 1, and once again let's go and throw inside of here the value of 9, and then we'll show an example of what exactly is going on. And in register 2 we're going to throw in a value of 8, and then we'll use TST to show you how this is working. So we'll go R1 and R2, and this is going to compare those values and set our flags. Then what we're going to do is we're going to say if these values are equal, we want to jump to our label, and that label is going to be called bit set. Remember, what this is going to do for us is subtract 8 from 9 and then set those flags, and we'll be able to check them. Otherwise, we're going to store the value of 1 inside of register 0 and then skip out of this by calling end. Now we know those aren't equal, so we're not going to get the bit set, but let's define it anyway. Store the value of 0 inside of R0, so we'll be able to see the results. We know we're going to get a 1 back here, of course, though. And then close out of our program and open up the terminal. This time we want to echo information out on the screen, and of course we can expect a value of 1 to show up because those two values are not equal. And if we hit enter, you can indeed see that that indeed is true. Another thing you can do is there's another conditional operator called TEQ, and this is your homework. And this is basically called test equivalence, and what it's going to do is perform a exclusive OR on bits and then update the 0 flags. There's your homework. Figure out how to use test equivalence, or TEQ, to come in and check if two values inside of registers are equal or not. Okay, so there's an overview of some conditional operators. Now we're going to get into some more interesting stuff. We're going to cover looping. Let's come in Vim again. Now basically looping in other languages is going to follow this basic format. So you're going to have, let's say you wanted to loop to the value of 10. You're going to come in here and you're going to define a first value, which is going to be equal to 0, and you're going to define another one that's going to start off with a starting value of 1, and then you're going to come in and say something like while R0 is less than or equal to 10. Well, then you want to come in here and continue to increment the value of R0. So you're going to go R0 is equal to R0 plus 1. And that's what I'm going to show you how to do here now with assembler. So here we have global start again, and we're going to come down inside of the start area. Let's just come in here and delete some of this. Escape, capital V. Now inside of start, we're going to do basically the same exact thing. We're going to go into R0, and we're going to give that the value of 0. And then we're going to do the same exact thing here with R1. And then we're going to come in and we're going to say that we want to jump to a label called continue loop. Then we need to increment this, and we're going to call this guy loop. And I'm just going to use add, of course. So I'm going to go R0. Then we need to define continue loop. Here we'll do a comparison, which is just a subtraction. So we're going to subtract from R0 the value of 9. Then we want to check if it's less than or equal to, meaning if the value inside of register 0 is less than or equal to 9. And if so, we're going to jump back to loop, and then we're going to add or increment the value inside of register 0. We're going to continue doing that over and over again until we reach a point in which the value stored in register 0 is greater than the value of 9. So we're doing exactly the same thing there that we did right here. And if you look at it, you can see that both of those are quite similar to the way they look. And we have that value stored inside of there, and if we execute this guy, then we should be able to come out here and then get a final value of 10. And if we come in, make that, and then run it, you can see that's indeed what we did. So there's a really simple loop just to get you used to loops. Once again, go in there, experiment, and see what other things you can do. Of course, in the next part of the tutorial, we're going to cover functions, and very, very soon we're going to be making some real-world programs. Just wanted to ease you in though into how we would loop and give you a little bit of an idea of how we would translate from a language like Python into assembly code and how those two things mix up. So now we're going to take a look at conditional codes. Now here you can see a whole list of conditional codes. Now basically what this is going to allow you to do is to define if an instruction is going to be executed based off of conditions. And these are all the different conditions you have here. Don't try to memorize this, there's no point. And what's neat about it is you're going to be able to do this by just ending at most any of these instructions with either of these codes that you have here, what you want to check for. So I'm going to show you here an example of exactly how these work out. And what I'm going to do here now is I'm going to show you in Python how we would increment a value that is stored in register 0 until it is equal to a value that is stored in register 1. And then we can show you the assembly language that's going to go along with that. So let's say we come in here and we want to say for the variable r0 we want to store a value of 50 inside of it, and in r1 we want to store a value of 2 inside of it. Then we would continue cycling through this guy as long as whatever the value is inside of r0 is greater than whatever we have inside of r1. And then we would come down inside of here, and instead we would come in and go r0 and say that we want to decrement that over and over again until this condition is no longer true by a value of 2. Now how exactly would we do that in assembly? I'm going to do it in much the same way. Come in to start, we're going to go inside of r0 and we're going to change this to 50. We're going to change this to 2, and then we're going to call a function called loop, or label called loop. Then going to come in, create another one, and this is going to decrement. So here what we want to do is we want to do a subtraction. But what we're really saying here is if r0, or the value stored inside of register 0, is greater than r1, we want to then subtract 2. So we built the condition directly inside of the instruction that we're giving. And there we go. Now down inside of the loop structure, we can then do a comparison between those two values by doing a subtraction, r0 and r1. And then basically we're going to say if they are not equal, we want to continue decrementing. And to do that is to say branch if not equal. That's what we're saying right there. Then we want to call the decrement label. And of course, let's go again and get rid of the continue loop again, because that would cause a catastrophe. And there you can see it went and decremented the value of 50 until it got to the value of 2 for whatever was in register 0, and once it did that, it exited completely out of there. So go in there and experiment running these other different instructions that you know by using these conditional codes and see what else you can come up with. Like I said, as the tutorial continues, I'm going to continue to add on to this knowledge, but I'm just in the beginning stages here, and a lot of experimentation is going to go a long way on your part. So now let's take a look at the barrel shifter. Now basically, the barrel shifter is going to make it very easy for us to move bits left and right, which is going to make it very easy for us to multiply and divide values. First guy we're going to talk about here is what's called LSL, or the logical shift left. And like I said, it's going to shift all our bits left and move the highest bit into the carry flag. And with it, it's going to be very easy for us to multiply times 2. So let's come in and let's get to start. And inside of register 1, we're going to give that a value of 15, which is going to be equivalent to 11111. And then inside of register 0, we'll move the value of r1, but shifted to the left by 1. So what this is basically saying is we want to shift the value inside of r1 1 bit and then save it inside of register 0. Capital V, get rid of all this stuff, do a make, and you can pause the video here for a second to see if you can guess what the result's going to be. And there you can see the result comes back as 30. And why is that? Well, if you take the value of 1 plus 2 plus 4 plus 8 plus 16, that's going to give you a value of 31. And then, like I said before, whenever it does a logical shift left, it is going to zero out the rightmost digit in binary, and that's the value of 1. So it comes out to 31 minus 1, which equals 30. Well, hopefully you got that answer, or that little question right. And now let's take a look at the logical shift right. Now this is the LSR command, and it's going to shift all our bits right and then move the lowest bit into the carry flag. And this is going to make it very easy for us to do divisions by 2, and it's going to work in much the same way. So we'll come down here, and in register 1 we're going to store 15. Do exactly the same stuff here, except in this situation we're going to come in, change this to LSR1, and this is going to shift the value in R1 1 bit right and then save that into R7. and then save that into register 0. So we're giving it a value of 15, and we're going to escape out of this. And while I do this, you can take a wild guess at what the answer is going to be. It's a little bit tricky. You might not get it, and that's okay. We come in here, hit enter. It's going to give you a value of 7. So it's going to take 15 and it's divided by 2, which is going to give us a value of 7.5. And then it's going to get rid of that fraction. So that's a little introduction into shifting, and we're going to get a lot more into that as the tutorial continues. And now we're going to get into something a lot more interesting, which is called memory storage. Now basically we have been storing data in registers for the most part, but now we're going to be able to store it in memory. And we're going to store data by referring to that data's address in memory, like we have been doing on and off here, but now we're going to get into the meat of it. So basically we're going to be storing an address in a register and then use that register to load as well as store data. And the labels we have used are going to be addresses that are going to refer to code, but we're also going to be able to use them to refer to data. So let's come in here and let's open up Vim once again. And the very first thing we're going to do is we're going to come in here and we're going to create two 4-byte variables and give them values. So we're going to be putting data in first, so we have to put the data block inside of here. And we're going to say that we want to request 4 bytes for our data, and balign does just that. We are then going to give it the name of 15. We're going to say that this is a word, and we want to start off by giving it the value of 15. So we're assigning 15 to 15. And then do another balign for 4. And now we're going to be storing 30 inside of here. Once again, this is going to be a word, and it's going to start off with a value of 30. Now we're getting into the assembly language part of our code here. So we're going to type in text, global start. We're then going to have to come down here at the very end of it and provide labels for the addresses in our data section. And to do so, we'll just call this address. It doesn't matter what you call this. This is just what I'm calling it. So I'm going to call it address 15. And this is a word lined up with 15. And then we're going to do exactly the same thing with 30. Once again, word and 30. And then come back up inside of the start area. And then if we want to load our address, we just go LDR. R1, refer to address 15. If we then want to come in here and load data using our address, we can go R1 and get that information from R1. LDR again, register 2, load our address, and then load the data using the address, R2. And then we'll be able to come in here and add this just to make sure that it works. So in register 0, we will store the addition of the values that are in R1 and R2. End is always the way that it was. Jump out of there, do a make, and there you can see as your result is 45. So let's go and do a little bit more here with storing information inside of memory. And we're going to do a lot more of this actually as the tutorials continue. Because what we're going to do now is we're actually going to come in and load values by referring to the addresses using another instruction called str. So here we can keep everything exactly the same. We got all of these all set up exactly the same way. We're going to request 4 bytes for our address. We're going to define storage for 15, except in this situation what we're going to do is instead of having the value of 15 inside of there, we're going to have that be 0. And then likewise, we're going to give this the value of 0. So we're going to use the address to store values in those addresses inside of memory. And so to do so, everything else here is going to be exactly the same. We're going to come in here and we're going to load the address just like we did previously. Except in this situation, we're going to put 15 inside of R3, or inside of register 3. So there's 15. And then like I said, we're going to store the value inside of register 3 inside of the address that is going to be stored there. So this is how we load information out of an address, and this is how we load information into it. So we're saying we want to take the value that is inside of register 13 or 15 and store it at the address in memory that is at R1. And then likewise, we don't need to do any of this stuff. Come in here, get rid of this, and instead we're going to do a copy. Once again, capital V, select all those different things, and copy is Y. Down here where we want to paste it, and capital P. This time we're going to be using register 2 though. Insert 2. This time we'll point at the address for 30. We're going to be storing 30 inside of here, of course. Then we'll take the value in the register there, and let's store it in register 2. And now that we have that done, we can come in here and add once again R0, R1, R2. Everything else here is exactly the same. and you're going to see that the result is exactly the same. And that came out as 68. Let's go in here and see why that happened that way. Oh, I see exactly what happened. Basically, what I did was I loaded that information inside of there, but I did not then come in and take the information out. So let's come in here like this. Now what we're going to need to do is come in here and basically do exactly what we did in the last part of the program. Should have copied that if I would have thought about it. So up here what we did was we went and stored the values inside of those two different registers, or those two addresses inside of memory. Now what we want to do is come in and add those values together. LDR, R1. Again, we're going to return or refer to those places in memory, and we're going to load those in. First we want to load the address. Use a LDR again. Register 1. Going to get the value outside of there and then store the value inside of register 1 once again. LDR, R2. Store, get that memory address, store it inside of R2. LDR, R2, and then get the value that is stored at that address by putting those brackets around it. And now I'll do an add, and now it'll work. I'm sure you know what the answer is going to be. Once again, everything else is exactly the same, and we should get a value of 45, and we did. Okay, so now that I showed how easy it is to make a dumb mistake inside of Assembler, I think I should cover debugging, which is what I'm going to cover next. So what I have here is, we saw this previously. All this is going to do is start off with a value of 0. It's going to increment by 1 each time. It's going to continue incrementing over and over again because we're going to compare what's in register 0 to the value of 9. And at the point in which what is in register 0 is going to be greater than or equal to 10, that's when we're going to exit our program. So what we're going to do here is we're going to step through our program and we're going to watch exactly how things are going to change. So we got that saved, and let's jump out of here. Now whenever you're compiling your program, if you want to debug, you're going to add the G option. So we're going to go AS and we're going to go G and 0, and then everything else is going to be the same with assembly tut.o, assembly tut.s, and we're going to make a makefile here in a second, and then you're going to go ld-o assembly tut and assembly tut.o. Now you're going to start the debugger by going gdb and assembly tut, and there you can see it all started out. Now you can list the first 10 lines of your program by just typing in list, and there you can see printed out the first 10 lines on your screen. And then you're going to be able to disassemble your code, and to do that you just type in disassemble, and let's say we wanted to start at start, and there you can see exactly, it's just showing you what is assigned to the start label. And if you want to know what this stuff is, right here the first number is going to be the location in memory for this instruction. And then right here what you're going to see is the number of bytes from the beginning of the label or your functions. Whenever we get into functions, you're going to get more into that. Now by using what are called breakpoints, you're going to be able to step through your code one line at a time and see how register and flag values are going to change. So let's come back here and let's do list again, and you can see all these different guys. Now let's say that we wanted to set a breakpoint right here at this looping part. We could do so by just typing in B and 13 for line 13. We could also delete a breakpoint by typing in delete 13, but we're not going to do that right now. And then we're going to type in run, and we're going to see exactly how everything's going to change as we cycle through this. Now after typing in run, we're going to go info R, and this is going to return all of our current register values at that point inside of our program. And you can see exactly how everything changed. Basically R0 starts off at 0, that's the way we set it, so it has a value of 0, and R1 is going to have a value of 1. You can see down here at the stack pointer that this is going to point to the stack inside of our memory. And then you could also see down here in PC, see right there where it has continue loop, this is going to store the next instruction we're going to execute. So you can literally sit here and just watch all of these different things move around in all these different registers, which is really kind of neat. Now if you want to see how things are going to change, what you got to do is just type in continue, and it's going to cycle through again until it hits the next breakpoint. So you know all these register values, so we'll hit continue, and then we'll type in info R again. And now you can see that the value for register 1 has incremented to 1. You can also notice here, if you look down in the CPSR, this guy right here has a value of 8. And what that tells us is the negative flag has been set, And the reason that was set is because compare what was in register 0 to 9. And the top flag in that situation is going to be equal to 8. And if we bounce over here, you can see that. See? 1, 2, 4, 8. So since it had a value of 8, well, you know indeed that this negative flag has been set. Now, of course, if you want to quit out of this, and you can continue cycling through it just by hitting continue over and over again and info R to watch everything change. And you could set multiple different breakpoints as well. I'm going to quit out of that by typing in quit, but I'm also going to come in here and change my make file so it's a little bit easier to debug, and we're going to be debugging more as the tutorial continues. So what I'm going to do here is I'm going to come in and say debug, and remember we're going to type in a tab after this, and then we'll go ASGO, and I'm going to do assembly tut, tab in again, LD, don't forget that tab, and assembly tut. And then we can actually run the debugger also. So gdb, assembly tut, and escape out of that, and do that. And now what we'll be able to do is just go make debug, and it's going to automatically open up the debugger. Okay, so like I said, just a brief overview of debugging. If you want to learn more about it, just experiment with it. Watch the different register values change for all the code we've covered in this tutorial and the previous tutorial, and you'll learn a lot more about how things are moving around inside of the registers. And as the last part of the tutorial, what I want to do is get back into memory storage and do a couple more complicated types of examples here. So let's go in to Vim once again. Now, of course, having a good understanding on how to use memory to store information is going to be very, very important because we want to keep our registers clear so we'll be able to perform our operations and then store data inside of memory. But to be able to do so, we're going to have to be very careful in regards to how we store data in memory. What I want to do now is cover ADR, and basically the directive ADR is going to load a 32-bit address by passing in a label. So we're going to go R0 and info. Let's go and create that. And basically it's just going to load the address for the data inside of register 0. Then we come down here after end, and let's just type in info and word and give it a value of 10. And you're going to see all this is going to do is just load this value of 10 into register 0 and then output that on the screen. But we're going to use the debugger just to look at this very specifically. So we're going to save that, and we're going to say make debug. Now we can put a breakpoint. Well, let's go do a list, see exactly what we got here. Now let's say we want to see exactly what's going on here register-wise whenever we get to line 6 inside of here. So we're going to throw a breakpoint at B6, and then we're going to go info R. Of course, we have to type in run first, and then info R. And there you can see right here that we indeed have the address stored inside of this guy, inside of register 0. But what's interesting is, let's say that we wanted to come in here and examine 4 words worth of data starting at the address for start. We could do that inside of our debugger. And to do so, we would just type in X and then 4 words and then underscore start. And you can see all these different guys. And also what you can see is the 10 value that we had right there. Let's quit out of that. Back inside of Vim. And basically what we're going to do is we're going to read data using LDR and write it using STR like we saw earlier in the tutorial. And to do so, you're going to hold the address for the information in memory inside of a register. So let's come in here, get rid of this guy. And let's say we want to load the address for the data into our R3 register. We would just type in LDR, R3 equal to info, and then we can get the value stored in that address by going LDR, store this in register 0 by just putting these brackets around it like that. WQ, make, and run it and echo, and you can see the 10 comes out there. It is, however, very important that whenever we're messing around inside of memory that we request enough space to allow for changes in values. And if you do not do that, you're going to get what's called a segmentation fault. So let's come in here and let's create another one of these guys. And we'll create a data section here at the top. And we're going to say that we want to request 4 bytes for our address. And then go info, because we're going to be changing the value here. So we got info. This is going to define the storage for info. Word, and 10 is going to be the value that we want to assign to this guy. Since we have data up there, we're going to have to say text so that we know where our assembly code is going to start. Then we'll come down here into the start label part. Once again, we're going to load the address for the data into our R3 or our 3rd register. And then after we do that, we want to come in and let's say throw the value of 100 into register 4. Then we can come and move 100 into the address space inside of memory. So we'll go and get the value that's stored in register 4 and store it in register 3. And then once again load the data that is stored in register 3 back into register 0. And then we don't need this guy down here. This would cause confusion actually if we kept this here. And there you can still see that we were able to store 100 inside of there. So that's how we were able to go in and find a location in memory and then store information inside of it. But make sure you have enough space whenever you are writing that code. Otherwise, like I said before, you're going to get a segmentation fault. Now, another thing that's going to be really interesting is we're going to be able to retrieve the next piece of data in a list by adding or subtracting values from a target address. Now, with something called pre-indexed addressing, you're going to be able to provide the base address and then the offset to the next value. And I'm going to show you exactly how that works. So let's say we have data inside of here again, and just get rid of this. What we're going to do here is create a list, and it's going to have primes inside of it. And I'm going to go word 2, word 3, word 5, and word 7. Text is all fine. Now we want to come in through here and cycle through all this information. So what we're going to do the first time is we are going to load the address for the data into R3. But again, this is going to change to primes because that's the address we're loading from. And now we can do a couple different things here. So let's go get rid of this. And I'm going to put this as a comment. You can go through and test these. But basically, if I would type in LDR, R0, and load in R3, this is going to get the value that is assigned at the address. We could, however, come in here and get the next item inside of our list by going LDR and load this in register 0, and then type in that address, followed by a comma, and then a 4. Because remember, we were storing words inside of there. And then this one will actually just grab it. This situation, we're going to come in and grab the next item inside of our list, just to show you how that works. And to grab the next, it's going to be a multiple of 4, which is going to give us a value of 8. And remember these prime numbers here, 2, 3, 5, 7. Just take a guess which one's going to show up. Type in make, and there you can see 5 showed up. Let's jump back over there just to make sure. And there you can see 2, 3, 5. So this guy right here is going to give us the value of 2. The next one is going to give us a value of 3 and 5. And then you can take a wild guess at what number you're going to have to put in here to get the next value. So that's how we can work with lists of different information that's stored inside of assembly as well. And of course, there's going to be other things. And in the next part of the tutorial, I'm going to talk about something called the stack. Another thing that's kind of interesting is we're also going to be able to come in and read and write bytes of information using another instruction called LDRB, B for bytes. So let's go in here to our data section again and just change this up a little bit. Let's put this at the bottom just to do something different. So what I'm going to do now is go down into our data section and define numbers. And this time we're going to be working with bytes. And this is just going to be a list of numbers. You can also work with half words, by the way. So to work with a half word, instead of typing in byte inside of there, you would type in HWRD. So there's more homework. Give that a try. Now how this would change is we can go up here to R3. And of course we're going to come in and change this to numbers because that's what we're working with now. However, if we wanted to come in here and grab the next one in the order here, we would type in LDRB. This is going to load the first byte or the very first number, whatever you want to refer to it. Again, B. This is going to load the next one inside of there, except this is going to be changed into a 1. And then this one here is going to load in the next one, or 2. So what we're going to show on our screen, take a wild guess which one of these values is going to show up. Let's save it, and we'll see if we're right. And there's 3. So that's how we're able to read in different lists of information. Kind of useful, kind of neat. Now you're also going to be able to come in here and for our final example, I'm going to show you how to load multiple words in registers using block transfer back in Vim. Here we're going to use ADR just like we did previously. And just cycle all that stuff, delete that out of there, insert. To do this properly, however, we're going to have to come in and enforce our 2-byte alignment. So I'm going to go dot align 2, leave this be numbers, and let's change this to words instead. So there's word, and we'll just have this be 1, 2, 3, and 4. And then up inside of start, we're going to go ADR and we want to get our address by passing numbers inside of there. But then we're going to do a block transfer. What it's going to do is it's going to take all 4 of these values we have right here and then store them in the registers R5 the whole way through R8. It's going to do that on one line of code. What you do is go LDMIA, R3, which is going to point at the address we're going to load the information from, and then we're going to say we want it in register 5 the whole way through register 8, and then just to show that that was able to output that information properly, inside of register 0 we're going to store whatever is in register 6, which is the value of 2 right here. Escape out, do another make, execute, and there you can see is 2. Okay guys, so there is a whole bunch of information. We're slowly but surely getting into real programs inside of assembly language. So just take a look at the information that I linked to in the description, work your way through it, do the little homework, little things that I talked about, and experiment a lot, and assembly language is going to make a whole lot more sense to you. So like always, please leave your questions and comments below. Otherwise, till next time.